Let's add a bit more meat to this idea of EKman pumping and interior flow. We'll keep revisiting this a few times. So we have looked at the surface currents already for the Pacific with colors and contours of sea surface temperature, and for the Atlantic. Both have many similar features: upwelling and cold temperatures, upwelling and cold temperatures, warm waters on the west, warm waters on the west, subtropical gyres, obviously having the Gulf of Guinea and the West African coast so close in the deep tropics add some differences here. So we have anticyclonic flow and EKman pumping and southward transport here, which we wrote as beta Vg equal to F dWdz. dWdz can be simply written as W EKman divided by h, as we will see, because the velocity at the surface of the ocean is 0. We already talked about how small velocities in the vertical of the order of 30 meters per year introduced horizontal currents of centimeter per second because of this amplification by beta over f, which is almost 1,000. We'll see that again. Okay, so you can see here that the surface current speeds are of order of tenths of centimeter per second, with some much faster currents at the western boundaries. Indian Ocean is, as always, different. We also have to explain why the currents are strong on the western side and not on the eastern side. The simplest way to think about it is, of course, that we have mid-latitude westerlies and tropical easterlies. So you have flow being pushed to the east by the westerlies, to the west by the easterlies. You have Coriolis, either using the beta Vg relation or just using Coriolis. You can infer that there has to be a southward transport in the interior. Okay, just by looking at the continuity of the circulation, you can argue that the flow here has to go north in the west. So you have to have a northward transport to compensate for the southward interior transport, just for continuity and mass balance, right? So the other way to look at it is to say that the solution that can mathematically allow you to have a northward transport here to compensate for this southward flow would actually require you to do negative work, which is not possible, which is not physically reasonable unless there is strange energy cascades happening, right? So this just argues that to sustain circulation against frictional dissipation at the bottom and side boundaries of the northward transport that is going to happen at either the western boundary or the eastern boundary, the wind stress must do work on the ocean, right? Since the rate of doing work is proportional to the product, the wind stress and the current velocity, u dot f has to be greater than 0. These two quantities must on average be in phase for the work done to be positive. This is the possible only when you have western boundary currents happening on the western side of the ocean basin. It's kind of a heuristic argument, but nonetheless, in reality, we know that the currents on the east are broad, shallow, and weak. They bring cold temperatures from higher latitudes toward the tropics, whereas warm tropical waters are being carried to the north by the strong, narrow, deep western boundary currents. This is the North Brazilian current we had seen, sheds off rings, gets into the, actually splits here and becomes the Antilles current, and the Caribbean current gets into the Gulf of Mexico, sheds a lot of so-called loop currents, becomes Florida current between Cuba and Florida, and then becomes the Gulf Stream and the North Atlantic drift, going off into Norwegian seas, Iceland and Greenland, Iceland Sea and Greenland Sea. Okay, We'll see what the transport is here, but I can just tell you that it's almost 250 times the transport in the Amazon River. That's massive amount of water being moved by the western boundary current here. Okay, so that's a kind of a brief introduction to how the anticyclonic gyre is set up by the westerlies, easterlies, interior southward transport caused by EKman pumping into the interior below the EKman layer, and the matching northward transport in the western boundary current. Okay, we'll visit this western boundary issue again a couple of more times, because that is one of the more important concepts in oceanography. Again, depends critically on the beta effect. Henry Stommel was the first one to show this in, I think, the 1940s. Imagine, before that we didn't know why there was western boundary current, even though Ben Franklin had already mapped the Gulf Stream as we talked before. Okay, so Stommel was the first one to show the role of beta, the variation of Coriolis with latitude, in creating this western boundary intensification.